Sagittarius A star, the supermassive black hole at the center of our galaxy, may have determined how large the Milky Way became. The M-sigma relation, a correlation between black hole mass and the velocity of stars in a galaxy's central bulge, suggests that galaxies and their central black holes are bound together, their fates linked through processes we are only now beginning to trace. Since 2023, the James Webb Space Telescope has returned data that challenges the standard model of galaxy formation, revealing black holes in the early universe so massive, so disproportionate to their host galaxies, that they could not have formed through the mechanisms we assumed. Black hole feedback, the process by which energy from a feeding black hole either suppresses or triggers star formation, appears to operate differently in the young universe than in the old one. And the heavy seed hypothesis, the idea that some black holes formed not from dying stars, but from the direct collapse of enormous gas clouds within dark matter halos, now carries support from observations that were, until recently, impossible to make. What follows is an examination of the evidence. By the end, you will understand how a single object, smaller than our solar system, containing less than 1/100% of our galaxy's mass, may have set the upper limit on how many stars the Milky Way could ever produce. If this channel is the kind of content you return to, consider subscribing. There is no algorithm shortcut for depth. Let us begin with what we thought we knew. For most of the 20th century, black holes were theoretical. They existed in equations, solutions to Einstein's field equations that most physicists considered mathematical curiosities, not physical objects. The idea that something could be so dense that not even light could escape was first proposed not by Einstein, but by an English clergyman and natural philosopher named John Michel in 1783. Michel called them dark stars. Pierre-Simon Laplace, the French mathematician, arrived at a similar conclusion independently in the 1790s, and neither could have imagined what would follow. For over a century, the idea remained dormant, a curiosity in the history of natural philosophy. Then, in 1915, Albert Einstein published the general theory of relativity, a description of gravity not as a force, but as the curvature of space-time itself by mass and energy. The equations were complex, the implications vast. Within months, a German physicist working on the Eastern Front, Karl Schwarzschild, serving in the German army during the First World War, solved Einstein's field equations for a spherically symmetric mass. Karl Schwarzschild completed the solution in 1916, just months before his death, and what he found was a radius, now called the Schwarzschild radius, below which nothing, not even light, could escape. The equation is direct. R sub s equals 2gm over c squared. R sub s is the radius of the event horizon, the boundary beyond which escape is impossible. G is the gravitational constant, 6.674 times 10 to the negative 11 meters cubed per kilogram per second squared. M is the mass of the object, and c is the speed of light, approximately 3 times 10 to the 8 meters per second. For a mass equal to our Sun, the Schwarzschild radius measures about 3 kilometers, roughly 1.9 miles. For a mass of 1 billion suns, the kind of mass we now find in the centers of distant galaxies, barely 700 million years after the beginning of the universe. The Schwarzschild radius stretches to roughly 3 billion kilometers, About 20 astronomical units, roughly the size of our solar system, out to the orbit of Uranus. An entire solar system's worth of space sealed off. And yet, that object, massive, compact, sealed, occupies less than a rounding error in the galaxy it inhabits. Think about that for a moment. Let it settle. Sagittarius A star, the Milky Way's central supermassive black hole, carries a mass of approximately 4.3 million times the mass of the Sun. Its event horizon radius spans about 12 million kilometers, roughly 7.5 million miles, 17 times the radius of the Sun, or about 1/5 the size of Mercury's orbit. Scale the Milky Way down to the size of the continental United States, roughly 4,000 kilometers or about 2,500 miles across, and Sagittarius A star's event horizon shrinks to the size of a coin, a few centimeters within the entire country. And yet, the evidence now suggests that this coin-sized region, relative to the galaxy it sits inside, may have determined how large that galaxy became. This is not metaphor. This is what the data indicates. To understand how a supermassive black hole could influence something 100,000 light-years across from a region smaller than our solar system, we need to examine the relationship between black holes and their galaxies, a relationship that, for 25 years, rested on a single empirical law. In 2000, two teams, one led by Laura Ferrariza and David Merritt, the other by Carl Gebhardt and colleagues, independently published a discovery that would reshape our understanding of galaxies. Across nearly every galaxy they examined, the mass of the central supermassive black hole tracked tightly with a specific property of the galaxy's central bulge: the velocity dispersion of its stars. Velocity dispersion, represented by the Greek letter sigma, measures how fast stars in a galaxy's bulge move in random directions. A high sigma means the stars are moving fast, indicating a deep gravitational potential well. A low sigma means slower, calmer stellar motions. The correlation Laura Ferraris and Carl Gebhardt discovered was not loose. It was tight, and it followed a power law. The equation, in its empirical form, is this: m sub bh over 10 to the 8th solar masses equals k times sigma over 200 kilometers per second raised to the power p. M sub bh is the mass of the central black hole. Sigma is the velocity dispersion. K is a constant of order unity, and p, the power, was found observationally to be approximately 4 to 5. What this equation says is precise. A galaxy whose bulge stars move at 200 kilometers per second will host a supermassive black hole of roughly 100 million solar masses. Raise the velocity to 250 kilometers per second, and the predicted black hole mass climbs to about 320 million solar masses. Drop sigma to 100 kilometers per second, a smaller galaxy, and the predicted black hole mass falls to roughly 8 million solar masses. The scatter in this m-sigma relation, the deviation from the predicted line, amounts to only about a factor of 2. A factor of 2. In astronomy, where uncertainties often span orders of magnitude, a factor of 2 is disturbingly precise. This is the m-sigma relation. For a quarter century, the m-sigma relation has served as the central organizing principle of galaxy black hole science. What the m-sigma relation describes, though, is a pattern, not an explanation for why the pattern exists. A supermassive black hole contains, in most galaxies, roughly 1/10% of the bulge's stellar mass. In the Milky Way, Sagittarius A star, at 4.3 million solar masses, represents a minute fraction of the galaxy's estimated stellar mass of 100 billion solar masses. In the Andromeda Galaxy, the central black hole carries about 110 million solar masses, sitting inside a bulge of roughly 100 billion solar masses. The ratio holds. The ratio remains consistent. The ratio is also strange. Consider what this implies. The supermassive black hole occupies a region smaller than our solar system. The bulge extends thousands of light years. No physical mechanism exists by which the gravity of the black hole alone, which dominates only within a few hundred light years at most, could directly control stars tens of thousands of light years away. The sphere of gravitational influence of Sagittarius A star extends perhaps 2 or 3 light years from the galactic center. Beyond that distance, the black hole's gravity becomes a negligible fraction of the total gravitational field. And yet, across billions of years and billions of galaxies, the mass of the central supermassive black hole and the velocity dispersion of the bulge stars arrive at the same ratio. As if every galaxy, no matter its history, solved the same equation by the present day. That regularity demands an explanation. The explanation proposed in 1998 by Joseph Silk and Martin Rees, Sir Martin Rees, the Astronomer Royal, born in 1942, one of the pioneers of both quasar theory and the heavy seed concept, was feedback, specifically black hole feedback. The Silk-Rees model proposed a threshold condition. As a supermassive black hole grows by accreting gas, it radiates energy, often prodigiously, as a quasar. When the energy output from that accretion reaches a critical threshold, when the energy injected into the surrounding gas equals the gravitational binding energy of the gas in the bulge, the gas gets expelled. Star formation ceases. The black hole stops growing because it has exhausted its fuel supply. The threshold condition, simplified, is this. 1/2 V escape squared is approximately 4 sigma squared. V escape is the escape velocity from the galaxy's gravitational potential. Sigma is the stellar velocity dispersion. When the energy from the quasar output matches this threshold, the gas blows out. Star formation stops. The black hole goes dormant. This is the concept of negative feedback. The black hole grows. The black hole radiates. The radiation heats and expels the gas. Star formation stops. The black hole stops feeding. The galaxy stops growing. And the ratio, black hole mass to bulge mass, locks in. For 2 decades, this remained the accepted narrative. Supermassive black holes functioned as regulators. They set limits. They determined when a galaxy stopped producing stars by clearing out the raw material, gas, that stars form from. The M-sigma relation carried the signature of this self-regulation. The black hole operated as a thermostat, and when the temperature reached the set point, the system shut off. A clean model, elegant and incomplete. Because the M-sigma relation describes the local universe, galaxies as they exist now, 13.8 billion years after the beginning. The M-sigma relation captures a snapshot of equilibrium, a photograph of the finish line. It says nothing about the race itself. how galaxies and their supermassive black holes arrived at this ratio, and the history of how we discovered supermassive black holes in galaxy centers tells us something important about the assumptions we carried into the JWST era. In 1963, Dutch-American astronomer Martin Schmidt identified the first quasar, an object designated 3C273, as a star-like source with an enormous redshift, meaning it was incredibly distant and unfathomably luminous. By the mid-1960s, astrophysicists concluded that quasars were most likely powered by accretion onto supermassive black holes, the first evidence that black holes of millions to billions of solar masses might actually exist in the physical universe, not merely in equations. In 1969, British astrophysicist Donald Lyndon Bell published a paper proposing that many galaxies, including the Milky Way, contain massive collapsed objects at their nuclei. These dormant objects, Lyndon Bell argued, were the quasars of the past, active galactic nuclei that had exhausted their fuel and gone quiet. Donald Lyndon Bell's insight proved foundational, transforming supermassive black holes from exotic theoretical curiosities into an expected component of galactic structure. The implication was striking. Every galaxy might carry a dark engine at its center, an engine that was once active, once luminous, and that shaped the galaxy's history before falling silent. In 1974, astronomers Bruce Balick and Robert Brown identified a compact radio source at the center of the Milky Way, a source that would later be named Sagittarius A star. By the late 1970s and early 1980s, the small angular size and high energy density of this radio source made Sagittarius A star the prime candidate for our galaxy's own supermassive black hole. The hunt was on. Through the 1980s, astronomers used spectroscopy to search for rapid gas or star motions near galactic centers, indirect evidence for concentrated mass. In 1984, John Cormandy found evidence for a central dark mass in the Andromeda Galaxy, M31. A decade later, in 1994, using the newly repaired Hubble Space Telescope, astronomers observed a rotating disk of gas in the core of galaxy M87, the galaxy at the center of the Virgo cluster. The gas rotation speed, 550 kilometers per second at a distance of 60 light-years from the center, implied an enormous mass of approximately 3 billion solar masses packed into a region smaller than our solar system. This stood as one of the first definitive dynamical proofs that supermassive black holes are real, physical objects. 2 years later, in the mid-1990s, two independent teams began tracking individual star orbits around Sagittarius A star. Andrea Ghez, using the Keck Observatory in Hawaii, and Reinhard Genzel, using the European Southern Observatory's Very Large Telescope in Chile, spent years mapping the trajectories of stars in the galactic center. The star S2, with a 16-year orbital period, comes as close as 17 light-hours to Sagittarius A star, reaching speeds of 7,700 kilometers per second at closest approach. These orbits proved beyond reasonable doubt that 4.3 million solar masses concentrate in a space smaller than our solar system. Andrea Ghez and Reinhard Genzel shared the 2020 Nobel Prize in Physics for this work. The Megorian relation followed in 1998, an early study of 36 galaxies suggesting black hole mass correlates with bulge mass at roughly 0.6%. The scatter was large, but the hint was there. Black holes and galaxies are connected. In 2000, the M-sigma relation, tighter, sharper, more precise, confirmed that connection. The Silk-Rees feedback model provided the theoretical explanation, and for 2 decades the framework held. Galaxies and supermassive black holes co-evolve. The black hole regulates. Negative feedback sets the limit. The M-sigma relation captures the result. The M-sigma relation describes the endpoint, though, not the beginning. The M-sigma relation does not reveal whether the galaxy formed first and the black hole followed, or whether the black hole formed first and the galaxy assembled around it. The M-sigma relation does not tell us what happened at the beginning. And that is where the James Webb Space Telescope changed everything. The James Webb Space Telescope launched on December 25, 2021, a 6.5-meter infrared space telescope built by NASA, the European Space Agency, and the Canadian Space Agency, was built to see further back in time than any telescope before it. Its instruments, including the Near-Infrared Spectrograph, NIR-SPEC, and the Mid-Infrared Instrument, MIRI, led by George Ricci of the University of Arizona, can detect light from the first galaxies, light that has traveled for more than 13 billion years, stretched by the expansion of space from ultraviolet and visible wavelengths into the infrared. To grasp the scale of JWST's reach, the light from the most distant objects the James Webb Space Telescope observes left those objects when the universe was less than 500 million years old. Compress 13.8 billion years into 1 calendar year, and all of human recorded history would occupy only the last half-second before midnight on December 31st. The epoch JWST observes, the first billion years, would correspond to roughly January of that year. We are, in effect, archaeologists of January, using infrared light as our excavation tool. This period, the reionization epoch, spans roughly from 200 million to 1 billion years after the beginning, when the first stars and galaxies formed and their radiation reionized the primordial hydrogen gas that filled the universe. Before JWST, we knew of approximately 50 quasars at redshift greater than 6, galaxies so distant that their light departed when the universe was less than 1 billion years old. Ground-based surveys and the Hubble Space Telescope had found these primarily. The most extreme of these, like Quasar J 0313-1806 at redshift 7.64, hosted supermassive black holes of 1.6 billion solar masses when the universe was only 670 million years old. Quasar ULAS J1342 + 0928 at redshift 7.54 harbored a black hole of roughly 800 million solar masses when the universe measured 690 million years old. To grasp the scale of these black holes, a supermassive black hole of 1 billion solar masses carries a Schwarzschild radius of approximately 3 billion kilometers, 20 astronomical units, roughly the distance from the Sun to Uranus. Its Eddington luminosity, the maximum steady brightness it can achieve, reaches approximately 1.3 times 10 to the 47 ergs per second, or about 3.3 times 10 to the 13 solar luminosities. That output exceeds the brightness of 300 Milky Way galaxies combined. All of that energy emanating from a region smaller than our solar system. This energy, this colossal output from a compact region, makes black hole feedback possible at galactic scales. These numbers posed a problem, a serious problem. To understand why, we need to examine the maximum rate at which a supermassive black hole can grow. The Eddington luminosity is the maximum steady brightness a black hole can achieve when the outward pressure of its radiation balances the inward pull of its gravity on infalling gas. The equation L sub ed equals 4 pi gmm sub pc over sigma sub t. In its simplified numerical form, that is approximately 1.3 times 10 to the 38 watts times m over m sun. M is the black hole mass. M sub p is the proton mass, 1.67 times 10 to the negative 27 kilograms. Sigma sub t is the Thomson cross-section for electron scattering, 6.65 times 10 to the negative 29 meters squared. When luminosity exceeds the Eddington luminosity, radiation pushes gas away faster than gravity can pull it in. Accretion stalls. From the Eddington luminosity, we derive the Salpeter time, named after Edwin Salpeter, who, along with Yakov Zeldovich, independently noted the implications of Eddington-limited quasar growth in 1964. The Salpeter time is the doubling time for a black hole accreting at the Eddington limit. The equation T sub Salpeter equals the natural log of 2 times C times sigma sub T over 4 pgm sub p ETA. For a radiative efficiency of 10%, ETA equals 0.1. The Salpeter time comes to approximately 40 million years. 40 million years per doubling. Now consider a light seed, a supermassive black hole that began as the remnant of one of the first massive stars, a population 3 star, with an initial mass of perhaps 100 solar masses. Growing from 100 solar masses to 1 billion solar masses requires roughly 14 doublings. 14 times 40 million years equals 560 million years. The first stars are thought to have formed roughly 100 to 200 million years after the beginning of the universe. The quasars at redshift 7 exist when the universe measured roughly 700 million years old. That leaves, at most, 500 to 600 million years for a 100 solar mass seed to reach 1 billion solar masses. Barely possible. If, and this is the critical condition, if the supermassive black hole accretes at the maximum Eddington rate continuously, with no interruptions for the entire period, no pauses, no gaps, no periods of starvation, 500 million years of continuous maximal feeding. This is the part that stays with me, not because the physics is wrong, but because it requires perfection. Uninterrupted perfection across hundreds of millions of years. And the universe, as we observe it, does not operate that way. Gas supplies are intermittent. Mergers disrupt accretion flows. Black hole feedback itself can expel the very gas the black hole needs. The idea that a light seed could sustain Eddington rate accretion without interruption for 500 million years is not impossible, but it is strained. And so an alternative was proposed. Not to replace the light seed model entirely, but to offer a different starting condition. The heavy seed hypothesis proposes that some supermassive black holes did not begin as the remnants of dead stars. Instead, they formed through the direct collapse of massive, pristine gas clouds in the early universe. Clouds of 10,000 to 1 million solar masses, collapsing not into stars, but directly into black holes. These are called direct collapse black holes. Martin Rees first explored the idea in 1978, and researchers including Marta Volonteri and Priyamvada Natarajan, born in 1971, an astrophysicist at Yale and one of the leading proponents of the heavy seed hypothesis, developed the concept further in the 2000s. The conditions required for a direct collapse black hole are specific: a pristine gas cloud, free of metals, in a dark matter halo massive enough to cool through atomic hydrogen processes, but suppressed from forming normal stars, perhaps by an intense external ultraviolet radiation field that prevents molecular hydrogen from forming and fragmenting the cloud. When those conditions are met, the gas collapses monolithically. No fragmentation, no intermediate star stage. A direct collapse black hole of 10,000 to 100,000 solar masses, or possibly up to 1 million solar masses, forms in a single event. A heavy seed. The physics of direct collapse deserves closer examination because the conditions required are specific and their rarity is itself informative. For a gas cloud to collapse directly into a supermassive black hole rather than fragmenting into stars, two conditions must be met simultaneously. First, the cloud must carry enough mass, on the order of 10,000 to 100,000 solar masses of gas, and it must reside in a dark matter halo large enough to provide the gravitational potential necessary for atomic hydrogen cooling. This typically requires halo masses above approximately 10 to the 7th solar masses. Below this threshold, the gas cannot cool efficiently and simply remains as hot diffuse gas that does not collapse. Second, and this is critical, the formation of molecular hydrogen, H2, must be suppressed. In a normal primordial gas cloud, molecular hydrogen forms readily and provides the cooling necessary for the gas to fragment into small, dense clumps that become individual stars. When molecular hydrogen is present, the cloud fragments, stars form, and the resulting black holes are light seeds, the remnants of those first stars, with masses of perhaps tens to hundreds of solar masses. To suppress molecular hydrogen formation, the cloud must be bathed in an intense ultraviolet radiation field, specifically radiation in the Lyman-Werner bands, photons with energies between 11.2 and 13.6 electron volts. These photons dissociate molecular hydrogen before it can accumulate. The source of this radiation would be a nearby galaxy or star-forming region, close enough to irradiate the collapsing cloud, but not so close as to disrupt the halo itself. This is a narrow window. The cloud must occupy the right mass dark matter halo, sit at the right distance from a radiation source, carry the right metallicity, essentially zero, no heavier elements, and exist at the right cosmic epoch. Too early, and the first radiation sources have not yet formed. Too late, and the intergalactic medium has been enriched with metals that enable efficient cooling and fragmentation. Whether these conditions were met in a significant fraction of early dark matter halos, or only in a tiny minority, stands as one of the central questions in this field. The answer determines whether heavy seeds served as a common starting point for supermassive black holes or a rare exception. Recalculate the growth problem with this new starting point. A heavy seed of 100,000 solar masses needs only about 7 doublings to reach 1 billion solar masses. 7 times 40 million years equals 280 million years. That fits comfortably within the available time window, even allowing for significant interruptions in accretion. The mathematics is direct. The heavy seed hypothesis does not eliminate the need for accretion, but it removes the need for perfection. It provides a head start, a buffer against the interruptions and inefficiencies that characterize real astrophysical environments. Before I continue, consider what this implies. If heavy seeds are the correct explanation for the earliest supermassive black holes, then some of the most massive objects in the young universe, black holes of millions of solar masses, formed before most stars did. The black hole did not grow inside a galaxy. The galaxy grew around the black hole. That is a reversal of the standard narrative. And the James Webb Space Telescope has provided the evidence to support it. In November 2023, astrophysicists Akos Bogdan and Priyamvada Natarajan published evidence for what may be the clearest case yet of a heavy seed origin. Using data from both JWST and the Chandra X-ray Observatory, launched in 1999, a NASA space telescope designed to detect X-ray emissions from high-energy regions like black hole accretion disks and jets, they identified a galaxy at redshift approximately 10.3, gravitationally lensed by the galaxy cluster Abell 2744. The galaxy, designated UHZ1, existed when the universe was only about 500 million years old. The stellar mass of UHZ1 was estimated at tens of millions of solar masses, a tiny galaxy by any standard. The X-ray luminosity detected by Chandra, roughly 5 times 10 to the 45 ergs per second, equivalent to about 10 trillion times the luminosity of the Sun, indicated a supermassive black hole of 10 million to 100 million solar masses. The ratio of black hole mass to stellar mass reached approximately 1 to 1, 100%. In the local universe, that ratio sits at 1/10 of 1%. In UHZ1, it was 1,000 times higher. Priyamvada Natarajan and Akos Bogdan interpreted this as evidence for a heavy seed origin. A light seed, a 100 solar mass remnant of a population 3 star, would have needed to grow by a factor of 100,000 to 1 million in 500 million years, requiring sustained super-Eddington accretion with no interruptions. A heavy seed of 100,000 solar masses, by contrast, would need only a factor of 100 to 1,000, well within the range of standard Eddington-limited growth with the salpeter time. UHZ1 was one observation. Not an isolated one, though. And the pattern that emerged across multiple surveys told a consistent story. In mid-2023, early results from JWST's SEERS survey, the Cosmic Evolution Early Release Science Program, reported a galaxy designated SEERS 1019 at redshift approximately 8.7. The galaxy's stellar mass measured roughly 100 million solar masses, but spectral analysis revealed an active galactic nucleus, a feeding supermassive black hole, with a mass of approximately 10 million solar masses. 10% of the galaxy's total stellar mass belonged to the black hole. At this redshift, the universe was only about 600 million years old. A supermassive black hole of 10 million solar masses, already active, already detectable, in a galaxy barely larger than a dwarf. Sears 1019 hosted one of the earliest known active galactic nuclei. The JD's survey, the JWST Advanced Deep Extragalactic Survey, probed even deeper. In December 2024, Sandro Tacella and colleagues published in Nature the detection of a supermassive black hole at redshift 6.68 when the universe was about 800 million years old, in a galaxy identified through JWST's JADES survey. The black hole mass, inferred from a broad hydrogen alpha emission line, came to approximately 400 million solar masses. The host galaxy's stellar mass measured roughly 1 billion solar masses. The ratio, 40%. 40%. The supermassive black hole carried nearly half the mass of all the stars in the galaxy combined. In the local universe, the typical ratio falls below 0.1%. This black hole outweighed what the M-sigma relation would predict for a galaxy, with a velocity dispersion of 70 kilometers per second by roughly 400 times. And the black hole was quiet, accreting at only 2% of its Eddington rate. Nearly dormant. What the data suggests is this. The supermassive black hole had already finished its explosive growth phase. It had consumed or expelled so much gas during an earlier period of rapid accretion, possibly through super Eddington bursts, that it had effectively starved itself. The galaxy around it had not yet caught up. The stars had not yet formed in sufficient numbers to bring the ratio back to the local M-sigma value. The supermassive black hole grew first. The galaxy was still assembling. This brings us to the object called Virgil. In December 2025, George Ricci, born in 1949, professor at the University of Arizona and science team lead for JWST's mid-infrared instrument, MIRI, co-led with Pierluigi Rinaldi, a study of a galaxy observed approximately 800 million years after the beginning of the universe. In optical and ultraviolet light, Virgil appeared unremarkable, a small, ordinary early galaxy. In the mid-infrared, seen through MIRI, Virgil revealed something hidden, an obscured, overmassive, supermassive black hole, a quasar buried in dust, invisible to every previous generation of telescope. George Ricci stated that JWST's findings show that supermassive black holes actually get ahead of the galaxies in a lot of cases, overturning earlier assumptions that galaxies formed first and black holes followed. The implications of the Virgil observation extend beyond a single galaxy. In optical and ultraviolet light, the wavelengths that the Hubble Space Telescope observes, Virgil appeared unremarkable, an ordinary small galaxy in the early universe. Only in the mid-infrared, at wavelengths that MIRI can detect, did the hidden quasar become visible. The dust surrounding the supermassive black hole absorbs the optical and ultraviolet light emitted by the accretion disk and re-emits it at longer wavelengths in the mid-infrared. Without MIRI, the supermassive black hole would have remained invisible. We would have classified Virgil as a normal star-forming galaxy and moved on. This raises an unsettling question. How many other galaxies in the early universe galaxies that appear normal in optical surveys harbor hidden, overmassive, supermassive black holes. How many objects have we classified as ordinary that are, in fact, extraordinary? Based on JWST data accumulated through 2025, the answer appears to be many. Virgil is not an isolated case. JWST has now identified dozens of similar objects at redshifts between 6 and 8, compact, extremely red sources that have come to be known as little red dots. These little red dots appear around 600 million years after the beginning of the universe and seem to disappear by about 1.5 billion years, absent at lower redshifts. Their properties are consistent with small galaxies hosting dusty, rapidly growing supermassive black holes, obscured active galactic nuclei that standard optical searches missed entirely. The photometric properties of the little red dots suggest stellar masses of roughly 1 billion solar masses or less. Yet, if hosting active galactic nuclei, their supermassive black holes might reach 10 million to 100 million solar masses, implying black hole to stellar mass fractions of 1 to 10%, far above the local M-sigma relation. The debate over what the little red dots actually are remains ongoing. Some researchers initially proposed more exotic explanations: extremely dusty stellar populations, unusual emission mechanisms, or even speculative objects like dark stars. The accumulating spectroscopic evidence increasingly supports the interpretation that most little red dots are obscured, supermassive black holes growing rapidly in small, dusty host galaxies. Their disappearance at lower redshifts, the fact that no similar population exists at redshift 4, for example, is itself a clue. Something happened to them. They did not simply vanish. They transformed. Perhaps their supermassive black holes exhausted their gas supply and went dormant, allowing the host galaxies to continue growing through star formation and mergers until the black hole-to-galaxy mass ratio fell back toward the local M-sigma value. Perhaps they merged with other systems, their overmassive, supermassive black holes ending up in the centers of larger galaxies. Perhaps some of the little red dots are the progenitors of today's compact elliptical galaxies, small, dense, old stellar systems with large central black holes. Connecting the little red dots at redshift 6 to 8 with specific populations of galaxies in the local universe remains an active area of research. This is forensic work in the truest sense, tracing the lineage of objects separated by 12 billion years of cosmic time, with only fragments of evidence at each end and almost nothing in between. The little red dots carry significance for two reasons. First, they suggest that the overmassive black hole phenomenon is not rare, not limited to a handful of extreme quasars, but potentially common in the early universe. Second, they represent a population that was invisible to the Hubble Space Telescope, launched in 1990, a 2.4-meter optical and ultraviolet space telescope that, despite revolutionizing our understanding of supermassive black holes in the 1990s and 2000s, lacks the infrared sensitivity to detect these dust-obscured sources. We had a blind spot. For 30 years, we did not know these objects existed. The James Webb Space Telescope removed that blind spot, and what it revealed was a population of supermassive black holes that had outgrown their galaxies. Let me pause here and state what this means in plain terms. For 25 years, the prevailing model of galaxy formation held that galaxies and their central supermassive black holes grew together, co-evolution regulated by black hole feedback. The galaxy formed stars. The supermassive black hole grew by accreting gas. When the black hole became massive enough, its energy output expelled the remaining gas, stopping both star formation and its own growth. The ratio, black hole mass to bulge mass, locked in through this self-regulation. The galaxy came first, or at least grew alongside the black hole. The evidence from JWST suggests that in many early galaxies, this sequence ran in reverse. The supermassive black hole grew first, already massive, disproportionately massive, before the galaxy had finished assembling its stars. The M-sigma relation, as measured in the local universe, did not hold in the young universe. The scatter was enormous, and the direction of that scatter was systematic. Supermassive black holes were too massive for their galaxies, not too small, too massive. This is what George Ricci means when he says supermassive black holes get ahead of the galaxies. And this raises a question that cuts to the core of this investigation. If the supermassive black hole was already there, already massive, already feeding, already radiating, what did it do to the galaxy forming around it? The standard answer for decades was negative feedback. The supermassive black hole suppresses star formation, heats gas, drives outflows, prevents the galaxy from forming too many stars. The evidence for negative feedback in massive galaxies remains substantial. Quasars in large galaxies at moderate redshifts show clear signs of gas being expelled, star formation being quenched, and galaxies transitioning from active star-forming systems to passive, quiescent ellipticals. There is another mode of black hole feedback, though, and it changes the picture entirely. In 2011, Amy Raines, born in 1982, an American astrophysicist specializing in black holes in dwarf galaxies, discovered something that should not have existed by the conventional wisdom of the time. In the dwarf starburst galaxy Hennies 2-10, approximately 30 million light-years from Earth, roughly 9 megaparsecs, with a stellar mass of only 3 to 4 billion solar masses, a galaxy perhaps 20 times smaller than the Milky Way in diameter, only a few thousand light-years across. Amy Raines found a supermassive black hole of approximately 1 million solar masses. That alone was unusual. Dwarf galaxies were not expected to harbor supermassive black holes, especially not ones as proportionally large as this. The ratio of black hole mass to galaxy mass in Hennies 2-10 reached about 3%, roughly 30 times higher than the typical ratio in large galaxies. The truly significant finding arrived in 2022, when Amy Raines and her student Zachary Schutter published data from the Hubble Space Telescope showing something that challenged a fundamental assumption about black hole feedback. The supermassive black hole in Hennies 2-10 was not suppressing star formation. It was triggering it. A collimated outflow, a jet-like structure, extended from the black hole approximately 150 parsecs, roughly 490 light-years, or about 4.6 times 10 to the 15 kilometers. At the tip of this outflow, where the jet impacted a dense region of gas, a young star cluster was forming. The gas in the filament showed velocities of approximately 200 kilometers per second, with a sinusoidal velocity pattern consistent with a precessing jet or outflow. The star cluster at the tip contained tens of thousands of young stars, only a few million years old. This was positive feedback. The supermassive black hole was not destroying, it was building. This stands as the first direct evidence of positive feedback from a supermassive black hole in a dwarf galaxy. The historical significance is difficult to overstate. For decades, since the Silk-Reese model of 1998, since the discovery of the M-sigma relation in 2000, the textbook picture held that black hole output inevitably suppresses star formation. Hanai's 2 to 10 demonstrated that this is not universally true. Under the right conditions, a modest black hole, a small galaxy, dense gas, an outflow of the right velocity and geometry, the black hole's energy output can create rather than destroy. A comparison of energy budgets illustrates why this is possible. A star-forming galaxy producing 100 solar masses of new stars per year emits roughly 5 times 10 to the 10 solar luminosities in starlight. A modest quasar, a supermassive black hole accreting only a few solar masses per year, can easily output 10 to the 12 solar luminosities, roughly 20 times more. Even a moderately active supermassive black hole easily competes energetically with a vigorously star-forming galaxy. The question is not whether the black hole possesses enough energy to affect the galaxy. The question is how that energy couples to the surrounding gas, whether it heats and expels or compresses and triggers. The mechanism connects to a relationship known as the Schmidt-Kennicutt law, first formulated by Martin Schmidt in 1959 and quantified further by Kennicutt in 1998. The law states sigma sub SFR equals A times sigma sub gas to the power n. Sigma sub SFR is the star formation rate surface density. Sigma sub gas is the gas surface density. A is a constant, and n is approximately 1 to 1.5. What this law describes is direct. When gas compresses, the star formation rate increases. If an outflow from a supermassive black hole, a jet, a wind, compresses gas rather than expelling it, the local gas density rises. And when gas density rises, star formation follows. In Hanai's 2 to 10, the black hole's outflow carried the right strength, not powerful enough to blow the gas apart, but powerful enough to compress it into collapse. A delicate balance. In a larger galaxy with a more powerful quasar, the same type of outflow would have been destructive, heating and expelling gas, quenching star formation. Negative feedback. In this small dwarf galaxy with this modest supermassive black hole, the conditions were different. The outflow triggered collapse. The black hole sowed the seeds for new stars. When I first understood this mechanism, I had to stop. Just stop and sit with what it meant. For decades, supermassive black holes at the centers of galaxies were understood primarily as destroyers, the mechanisms that shut down star formation, that cleared out gas, that ended a galaxy's productive years. The M-sigma relation served as the evidence for this regulatory role. The black hole functioned as a ceiling, a limit, a termination point. Henai's 2 to 10 showed something different. In a small galaxy, the kind of galaxy that might resemble a proto-galactic building block in the early universe, the supermassive black hole was not a ceiling. It acted as a catalyst, not stopping star formation but causing it. The dwarf galaxy Henai's 2-10 is small enough that its black hole's influence is proportionally larger than in a system like the Milky Way. The supermassive black hole's mass, 1 million solar masses, represents about 3% of the galaxy's total stellar mass of 3 to 4 billion solar masses. In the Milky Way, Sagittarius A star represents about 4/1,000ths of 1%. In Henai's 2 to 10, the black hole is roughly 30 times more dominant proportionally, and that proportional dominance matters because the energy output from the black hole, even at modest accretion rates, can compete energetically with the total stellar output of the galaxy. The geometry of the outflow matters as well. The jet or wind from the supermassive black hole in Henai's 2-10 is not isotropic but collimated, directed. It strikes a specific region of gas, compressing it. If the outflow were dispersed in all directions, the effect would dilute, heating the gas broadly rather than compressing it locally. Because the outflow is focused, it acts like a finger pressing into dough, creating a dense region at the point of contact, and that dense region is where the stars form. The difference between positive and negative black hole feedback may come down to subtle details. The angle of the jet, the velocity of the outflow, the ambient gas pressure, the mass of the host galaxy, the distance from the black hole to the nearest gas cloud. It is a reminder of how much we do not yet understand, that a process as chaotic as a supermassive black hole jet can have such targeted effects. In one situation, it blows a cavity. In another, it compresses a filament. The outcome depends on initial conditions that vary from galaxy to galaxy, from epoch to epoch, from jet to jet. This remains an active research question. Until we can simulate and observe enough cases to build a predictive model, the boundary between positive and negative black hole feedback stands as one of the most important unknowns in galaxy formation science. And if that happened in Henai's 2 to 10, 30 million light-years away in the present-day universe, what happened in the early universe when galaxies were smaller, denser, richer in gas, and when overmassive, supermassive black holes were, by the evidence of JWST, common? The implications cascade. If early supermassive black holes, heavy seeds of tens of thousands to hundreds of thousands of solar masses formed through direct collapse in dark matter halos, existed at the centers of small, gas-rich protogalaxies, their outflows could have compressed surrounding gas. That compression could have triggered star formation. The stars that formed would have produced heavier elements, enriching the gas, enabling the next generation of stars. The supermassive black hole, through positive feedback, could have jump-started the entire star-forming life of the galaxy. This is not speculation unconstrained by evidence. Astronomers are now actively searching for additional cases of positive feedback beyond Henai's 2-10. Radio observations, including data from the Atacama Large Millimeter Array, ALMA, have found candidate jet-induced star formation in larger galaxies too. For example, jets from the active galaxy Centaurus A, whose nuclear X-ray source was first detected by the Uhuru X-ray satellite in 1971. In JWST data, astronomers are examining active galactic nuclei in small protogalaxies to determine whether surrounding regions show enhanced star formation, detected through specific emission lines like hydrogen alpha or ultraviolet spectral features that indicate recently compressed starburst regions. A developing notion has emerged: a black hole feedback life cycle. In low-mass systems or at early cosmic times, when galaxies were small and gas-rich, positive feedback may dominate. The supermassive black hole nurtures, triggers, builds. As the galaxy grows, as the black hole grows, a transition occurs. The energy output crosses the Silk Reese threshold. Positive feedback gives way to negative feedback. The supermassive black hole shifts from catalyst to regulator, from builder to terminator. In high-mass systems at later cosmic times, the large elliptical galaxies we observe today, negative feedback dominates. The supermassive black hole quenches, suppresses, ends the galaxy's productive years. And the final size of the galaxy, the total number of stars it would ever produce, would have been set by when that transition occurred, by how massive the supermassive black hole was when its feedback mode flipped, by, in a measurable sense, the properties of the black hole that formed at the center of the protogalactic cloud, before most of the galaxy's stars existed. One supermassive black hole, influencing the size of an entire galaxy. This is the narrative that the evidence now supports. Not fully confirmed, there are alternative explanations, ongoing debates, and significant uncertainties, but the direction of the data is consistent. The data points toward a model in which the central supermassive black hole is not a passive byproduct of galaxy formation, but an active participant, first a builder through positive feedback, then a regulator through negative feedback, and ultimately a determinant of the galaxy's final state. We can measure the distances, we can calculate the masses, we can map the structures. What set all of this in motion? Why these laws and not others, why these conditions and not others, remains unanswered. Science describes what happens and how it happens. The question of why anything exists at all, why there is something rather than nothing, sits beyond the reach of telescopes and equations. Let us now examine a specific case that demonstrates the extreme end of this story. NGC1277. NGC1277 is a compact lenticular galaxy, a small, dense galaxy located in the Perseus cluster that appears to have stopped forming stars long ago. Remco van den Bosch and colleagues studied NGC 1277 and reported their findings in 2012. The central supermassive black hole in NGC 1277 carries a mass of approximately 17 billion solar masses. 17 billion. Let that number register. 17 billion solar masses. That is roughly 4,000 times the mass of Sagittarius A star, in a galaxy that is smaller and less massive than the Milky Way. The host galaxy's total stellar mass comes to approximately 120 billion solar masses. The supermassive black hole accounts for 14% of the entire galaxy's mass, and because NGC 1277 is almost entirely bulge with no significant disk component, the black hole constitutes roughly 59% of the bulge mass. More than half the bulge is black hole. The Schwarzschild radius of a 17 billion solar mass supermassive black hole stretches to approximately 50 billion kilometers, roughly 330 astronomical units. That places the event horizon well beyond the orbit of Pluto. The entire inner solar system, out past the Kuiper belt, would fit inside this black hole's event horizon. In the local universe, the M-sigma relation predicts that a galaxy with NGC 1277's velocity dispersion of about 300 kilometers per second should host a supermassive black hole of roughly 2 billion solar masses. NGC 1277's black hole measures 17 billion, approximately 7 times higher than what the M-sigma relation predicts. An outlier sitting 7 times above the expected line. A violation of the rule that supposedly described all local galaxies. NGC 1277 appears to be a relic, a galaxy that formed a disproportionately massive supermassive black hole early in cosmic history, and then stopped. The black hole grew so large, so fast, that it expelled or consumed all available gas. Star formation ceased. The galaxy froze in place, a fossil from an earlier epoch, carrying the imprint of a supermassive black hole that overwhelmed its host. Other galaxies in the local universe show similar but less extreme patterns. The total mass density of supermassive black holes across all galaxies in the local universe measures about 5 times 10 to the 5 solar masses per cubic megaparsec. The stellar mass density reaches about 5 times 10 to the 8 solar masses per cubic megaparsec, roughly 1,000 times higher. Supermassive black holes are, by mass, a trace component of the universe's baryonic content. Look back to redshift 7, though, to the first billion years, and in some individual protogalaxies, the supermassive black hole-to-stellar mass ratio approached unity. The black hole was not a trace component, it was a dominant one. Over 13 billion years, these ratios balanced out, but in the beginning, the imbalance was extreme. If the M-sigma relation is the endpoint, the equilibrium that galaxies eventually reach, then NGC 1277 is a galaxy that never fully arrived there. Its supermassive black hole overshot the equilibrium, and the galaxy paid the price in arrested development. A warning written in the absence of new starlight about what happens when the black hole at the center wins the contest for gas. What would you conclude from this evidence? A pattern forms across these data points, NGC 1277 UHZ1, the Takela galaxy at redshift 6.68, Virgil, the little red dots. The pattern is this. In the early universe, some supermassive black holes reached masses that were grossly disproportionate to their host galaxies. In the local universe, those proportions have been corrected, either because the galaxies eventually grew to match their supermassive black holes through continued star formation and mergers, or because the black holes quenched their galaxies before they could grow further. NGC 1277 represents the latter outcome, a galaxy frozen by its own black hole. The Milky Way, with its modest Sagittarius A star and its ongoing star formation, appears to represent something else entirely. A galaxy where the central supermassive black hole never dominated, where the balance was maintained across billions of years, where the black hole was the right size at the right time. Now, consider what that means for the Milky Way. Sagittarius, a star, our galaxy's central supermassive black hole carries a mass of 4.3 million solar masses, roughly 8.6 times 10 to the 36 kilograms. Its distance from Earth spans approximately 26,000 light-years, about 2.5 times 10 to the 17 kilometers, or roughly 1.6 times 10 to the 17 miles. The Milky Way contains an estimated stellar mass of 100 billion solar masses and a total mass, including dark matter, of roughly 500 billion solar masses. Sagittarius A star contributes only about 0.06% of the Milky Way's total stellar mass. It sits quiet. It does not blaze as a quasar. It drives no significant outflows. The Milky Way still forms stars at a modest rate. The Milky Way sits comfortably on the M-sigma relation. The ratio of supermassive black hole mass to stellar mass reaches about 1 in 25,000, in line with the local average. Consider a counterfactual, though. If Sagittarius A star had been 100 times more massive early in the Milky Way's history, say 400 million solar masses instead of 4 million, what would have occurred? A supermassive black hole of 400 million solar masses actively accreting in a young, gas-rich Milky Way would have produced quasar-level luminosity. Its energy output, potentially on the order of 10 to the 46 ergs per second, near the Eddington luminosity for that mass, would have heated and expelled the gas needed for star formation. The Milky Way's star formation history would have been truncated, cut short, potentially billions of years earlier than it actually was. The galaxy might have become a quiescent elliptical, like NGC 1277, a dense red dead system with far fewer stars and no ongoing production of the heavy elements necessary for planets and complex chemistry. The Milky Way's ability to produce the generations of stars that forge carbon, oxygen, iron, and the other elements that constitute rocky planets depends in part on the fact that star formation continued for billions of years. That continuation depended, at least in part, on Sagittarius A star being small enough not to quench it prematurely. Pause and consider what that means. Every heavy element in your body, every atom of carbon in your cells, every atom of iron in your blood, every atom of calcium in your bones was forged in the interior of a star that lived and died before our sun formed. Those stars could only exist because the Milky Way continued forming stars for billions of years. And the Milky Way continued forming stars, in part, because Sagittarius A star, the supermassive black hole at the galaxy's center, did not grow massive enough, early enough, to shut that process down. If the black hole had been larger, if it had been a heavy seed of 100,000 solar masses that grew rapidly through super-Eddington accretion in the first few 100 million years, the Milky Way might have been quenched. Star formation might have ceased billions of years before the sun formed. The elements necessary for rocky planets and complex chemistry might never have been produced in sufficient quantities. The conditions that permitted the formation of our solar system 4.6 billion years ago might never have existed. This is not a claim about purpose. This is a statement about contingency. The conditions were what they were, and we find ourselves here observing them. The fact that those conditions, specifically the mass and accretion history of one supermassive black hole, could have been different, and that the difference would have been consequential, is worth sitting with. The supermassive black hole at our galaxy's center was the right size, not too large, which would have quenched the galaxy too early, not absent, which might have allowed the galaxy to form stars chaotically without the regulation that the M-sigma relation implies. The conditions were what they were, and we find ourselves here in a galaxy that still forms stars, orbiting a star that formed 4.6 billion years ago from gas enriched by generations of stellar nucleosynthesis, generations that were possible because the black hole at the center permitted them to be. The confirmation that these objects at galaxy centers truly are supermassive black holes described by general relativity possessing event horizons came through a different instrument entirely. The Event Horizon Telescope, a worldwide network of radio observatories operating together as an interferometer, effectively an Earth-sized telescope, produced the first image of a supermassive black hole's shadow in 2019. The 6.5 billion solar mass black hole at the center of galaxy M87, designated M87 star. The Schwarzschild radius of M87 star reaches approximately 19 billion kilometers, about 120 astronomical units, larger than our entire solar system. The rotation speed of gas around M87's core had been measured by the Hubble Space Telescope as early as 1994, 550 kilometers per second at 60 light-years from the center, implying an enormous mass packed into a tiny volume. The Event Horizon Telescope confirmed M87 star was indeed a black hole with an event horizon consistent with general relativity. In 2022, the Event Horizon Telescope produced a corresponding image for Sagittarius A star, our own galaxy's supermassive black hole. The shadow matched a 4.3 million solar mass object described by the Schwarzschild solution. These images are not photographs in the conventional sense. They are reconstructions from radio data collected simultaneously across multiple continents. They represent direct observational evidence for event horizons, the defining feature of a black hole. Before these images, the case for supermassive black holes rested on indirect evidence: orbital dynamics, accretion disk spectra, jet structures. After these images, the case rested on something as close to direct observation as the nature of these objects allows. These images did not directly inform how supermassive black holes formed, but they validated that the objects we study, the objects whose feedback we model, whose masses we correlate with galaxy properties, are actual black holes, not exotic alternatives, not theoretical constructs, real physical objects with event horizons described by the equations Carl Schwarzschild derived in 1916. Evidence from multiple instruments converges on the same picture. The orbits of stars around Sagittarius A star, tracked over decades by teams led by Andrea Ghez using the Keck Observatory in Hawaii and Reinhard Genzel using the Very Large Telescope in Chile, work for which they shared the 2020 Nobel Prize in Physics, proved that a mass of 4.3 million solar masses concentrates in a region smaller than our solar system. The star designated S2, with a 16-year orbital period, approaches within 17 light-hours of Sagittarius A star, reaching speeds of up to 7,700 kilometers per second at closest approach, about 2.5% of the speed of light. The data is consistent. The physics is precise. the supermassive black hole is real, and the question of its role in shaping the galaxy around it now stands as the central question in galaxy formation science. A deeper question sits embedded in this investigation, one that touches the limits of what science can currently address, and it concerns the feeding rate of supermassive black holes in their earliest environments. The Bondi accretion rate describes how quickly a black hole can consume gas from its surroundings based purely on its mass, the density of the surrounding gas, and the speed of sound in that gas. The equation m dot sub Bondi equals lambda times 4 pi g squared m squared rho over c sub s cubed. M is the black hole mass. Rho is the ambient gas density. C sub s is the sound speed in the gas. Lambda is a dimensionless factor of approximately 0.25 to 1, depending on gas properties. What this equation reveals is important. The accretion rate depends on the square of the supermassive black hole mass and the gas density, and inversely on the cube of the sound speed. In the early universe, where gas was dense and cold, high rho, low c sub s, the Bondi accretion rate could have been orders of magnitude higher than in the hot, diffuse gas halos of present-day galaxies. A 1 million solar mass supermassive black hole embedded in a cold, dense gas cloud with a density of 10 to the negative 24 kilograms per cubic meter, and a sound speed of 10 kilometers per second, about 6.2 miles per second, could accrete roughly 1/10 of a solar mass per year. Increase the density by a factor of 100, plausible in a dense primordial cloud, and the accretion rate rises proportionally. The early universe was suited for rapid supermassive black hole growth. Dense gas, low temperatures, abundant fuel. The conditions allowed heavy seeds, direct collapse black holes, to grow rapidly, potentially exceeding the Eddington limit for brief periods when the infalling gas was thick enough to trap the outgoing radiation before it could exert the outward pressure that normally stalls accretion. And that rapid growth, that super Eddington accretion, is precisely what the Tacella 2024 observation at redshift 6.68 suggests. A supermassive black hole that grew in short explosive bursts, overshooting what the galaxy could keep pace with, and then going quiet once it had exhausted its local gas supply. We see the aftermath. The supermassive black hole is massive. The galaxy is small. The ratio sits off by a factor of 400 from the local M-sigma relation, and the black hole rests there, nearly dormant, at 2% of its Eddington rate, a silent record of a violent past. Think about that. What we observe is not the event. It is the scar. A third seeding mechanism deserves examination, though it remains the most speculative: primordial black holes. The idea, proposed by Stephen Hawking, Yakov Zeldovich, and others in the 1970s, suggests that black holes could have formed not from stars, not from collapsing gas clouds, but directly from density fluctuations in the very early universe, fractions of a second after the beginning. If regions of space were dense enough during those first moments, they could have collapsed under their own gravity before any stars or galaxies existed. If primordial black holes formed with masses in the range of 100,000 to 1 million solar masses, they would function as ready-made heavy seeds. No special astrophysical conditions required. No need for pristine gas halos or ultraviolet radiation backgrounds or suppressed molecular hydrogen. The seeds would simply exist, embedded in the early universe from the earliest moments. The appeal is obvious. The problems are also significant. No direct evidence exists for primordial black holes in this mass range. Constraints from the cosmic microwave background and other observations limit their abundance, and the mechanism requires specific conditions in the very early universe, density fluctuations of a particular amplitude that are not predicted by the simplest models of cosmic inflation. Primordial black holes remain a possibility, but they are not the leading explanation. The evidence, as of 2026, points more strongly toward direct collapse black holes, heavy seeds formed through astrophysical processes in the first few 100 million years, supplemented by episodes of super-Eddington accretion. Not everyone is convinced that heavy seeds are the primary answer, though, and the counter-arguments deserve examination. Some researchers point out that super-Eddington accretion alone, without requiring heavy seeds, can effectively reduce the required growth time for a light seed. If a supermassive black hole accretes in certain regimes, for example, through what is called a slim accretion disk, where the gas is optically thick and photons become trapped before they can exert outward pressure, it can exceed the Eddington limit by factors of a few to 10 for short periods. If early supermassive black holes spent even a fraction of their time in these hyperaccreting states, that could boost their growth significantly. Theoretical support exists for this. Models of slim disk accretion, developed in the 1980s and refined since, show that when the accretion rate greatly exceeds the Eddington rate, the photons generated in the inner disk become trapped in the infalling gas flow. They are advected, carried inward, rather than radiated outward. The effective radiation pressure drops, and the black hole can swallow more than the Eddington limit would normally allow. Observationally, if a super-Eddington phase is heavily obscured by gas and dust, it would be difficult to detect in optical or ultraviolet light, but it might show up in X-rays or in certain mid-infrared spectral features. This is precisely the kind of signal the Chandra X-ray Observatory and JWST's MIRI instrument are designed to detect. Several active searches are underway. Merger-driven growth presents another possibility. In the dense early universe, black holes of intermediate mass, thousands to tens of thousands of solar masses, may have merged frequently. Each merger would produce a sudden jump in mass, rather than the gradual climb of accretion. Gravitational waves from such mergers might be detectable by LISA. If these mergers were common enough, even a modest light seed could, through a combination of rapid accretion and repeated mergers, reach supermassive scales within the available time. The honest assessment is this: the answer may not be a single mechanism. The evidence suggests a combination, heavier seeds and faster growth, operating together to different degrees in different environments. Some supermassive black holes may have formed from heavy seeds through direct collapse. Others may have grown from lighter seeds through super-Eddington accretion. Still others may have assembled through mergers. The question is, which path dominated, and JWST's statistical surveys, now in progress, are designed to answer that. This is where the investigation takes a turn that I find deeply unsettling. Not because the physics is uncertain, uncertainty is the normal state of frontier science, but because of what the data implies about how fragile the process is. How contingent, how dependent on conditions that could easily have been different. Consider what we know about the objects JWST is finding. The supermassive black hole in the Tachella 2024 galaxy, 400 million solar masses at redshift 6.68, accretes at only 2% of its Eddington rate, nearly dormant. Its mass reaches 40% of the galaxy's stellar mass. That supermassive black hole did not grow slowly and steadily. The data suggests it grew in explosive bursts, short periods of super-Eddington accretion, where infalling gas was dense enough to trap the outgoing radiation, allowing the black hole to consume far more than the Eddington limit would normally permit. And then it stopped. It went quiet. It starved. This is counterintuitive. You might expect that a more massive, supermassive black hole would simply eat more. The opposite can happen, though. A black hole that grows too fast can blow away its own food supply. The radiation and outflows from its accretion, the very mechanisms that make it detectable as a quasar, can expel the gas in its immediate vicinity. The black hole becomes too powerful for its own environment, clears the area, and then, with no gas left to consume, it goes dormant. It resembles a predator that overhunts in a confined ecosystem. After the feast, nothing remains to eat. The predator starves in abundance, surrounded by a galaxy that still contains gas at larger radii, but none close enough to fall into the black hole's gravitational influence on relevant timescales. This pattern, rapid growth followed by self-induced starvation, may explain why many of the overmassive, supermassive black holes JWST is finding are quiet. They are not currently active. They are not glowing as quasars. They sit there, massive and dormant, their presence revealed only by the subtle broadening of spectral emission lines or by their gravitational effects on nearby stars. If we had looked only for active quasars, which is what most surveys before JWST were designed to find, we would have missed them entirely. What we observe in these dormant overmassive supermassive black holes is the aftermath, the scar of a violent past, the evidence of a process that played out hundreds of millions of years before the light reached our instruments. This brings the investigation to a deeper question about the M-sigma relation itself. If the M-sigma relation is the endpoint, the equilibrium that galaxies reach after billions of years of accretion, feedback, mergers, and star formation, then the M-sigma relation is not a law in the way that the Schwarzschild radius equation is a law. The Schwarzschild radius follows directly from general relativity. The M-sigma relation is empirical, a pattern we observe. The fact that it exists at all, that billions of galaxies with vastly different formation histories, different merger trees, different gas supplies, different environments, all arrive at approximately the same ratio of supermassive black hole mass to bulge velocity dispersion, is, on reflection, strange. The processes involved are chaotic. Galaxy mergers are violent, stochastic events. Gas infall is irregular. Supernova explosions disrupt local conditions. Active galactic nuclei flare and subside unpredictably. And yet, When all of these chaotic processes play out over cosmic time, the result is a clean power law. M sub BH proportional to sigma to the fourth or fifth power, with scatter of only a factor of 2. How does chaos produce order? The Silk-Rees feedback model provides a mechanism, the blowout threshold. A mechanism, though, is not the same as an explanation. The mechanism tells us how the ratio is enforced once the black hole reaches the right mass. The mechanism does not tell us why the conditions exist that allow this enforcement to work. Does not tell us why the constants, the gravitational constant, the speed of light, the Thomson cross-section, the proton mass, combine in such a way that a self-regulating equilibrium is possible at all. We can describe the mechanism. We can model it. We can simulate it. The question of why this particular set of physical conditions gives rise to a universe where supermassive black holes and galaxies can reach a stable, reproducible ratio. That question sits at the boundary of physics and something deeper, something that the equations describe but do not explain. I return to this point often, not for comfort, for clarity. Let me now trace the full timeline of what happens to a galaxy, from birth to the present day, under this revised understanding. The forensic reconstruction. In the first 100 million years after the beginning of the universe, the first structures form. Dark matter halos, invisible scaffolding held together by gravity, collapse from the primordial density fluctuations. Gas falls into these halos, collecting at the centers, cooling and beginning to form the first stars. These are population 3 stars, massive, luminous, short-lived, formed from pristine hydrogen and helium with no heavier elements. In some dark matter halos, perhaps 1 in a million, perhaps 1 in 100,000, the fraction remains uncertain. Conditions differ. A strong ultraviolet radiation field from nearby star-forming regions suppresses the formation of molecular hydrogen. Without molecular hydrogen, the gas cannot cool efficiently enough to fragment into individual stars. Instead, the entire gas cloud, tens of thousands to hundreds of thousands of solar masses, collapses as a single entity. No stars form. The cloud collapses directly into a supermassive black hole, a heavy seed, a direct collapse black hole of 10,000 to 100,000 solar masses, or perhaps more. This heavy seed sits at the center of a small protogalactic halo, a dark matter structure containing gas, but not yet a galaxy in any recognizable sense. No significant stellar population yet, just gas, dark matter, and a newly formed supermassive black hole that is already, relative to its surroundings, overmassive. The black hole begins to accrete. Gas falls in. An accretion disk forms, a rotating structure of gas spiraling inward, heating through friction, glowing in X-ray and ultraviolet light. The supermassive black hole's luminosity increases. Outflows form, jets, winds, radiation-driven shells of gas pushed outward. And here the feedback life cycle begins. In this small, gas-rich protogalaxy, the outflows lack the power to blow gas out of the system entirely. The dark matter halo runs deep enough, the gas dense enough that the outflows cannot escape. Instead, they compress the surrounding gas. The local gas density increases. And, as the Schmidt-Kennicutt law predicts, sigma sub SFR equals A times sigma sub gas to the power n, higher gas density means higher star formation rate. stars begin to form. Not despite the supermassive black hole, but because of it. Positive feedback. The first stars born in this protogalaxy are triggered by the black hole's outflows. They forge heavier elements, carbon, oxygen, silicon, through nuclear fusion. When they die, they scatter those elements into the gas. The next generation of stars forms from enriched gas, and the process continues. The galaxy begins to grow. As the galaxy grows, the supermassive black hole continues to accrete. Its mass increases, its luminosity increases, its outflows become more powerful. At some point, perhaps when the black hole reaches a few million solar masses, perhaps tens of millions, the feedback threshold is crossed. The energy output from the active galactic nucleus exceeds the binding energy of the gas in the inner regions of the galaxy. The Silk-Reese condition is met. 1/2 V escape squared equals approximately 4 sigma squared. The gas gets expelled. Star formation in the central bulge slows or stops. The supermassive black hole, deprived of fuel, goes quiet. Negative feedback has replaced positive feedback. The builder has become the regulator. The galaxy does not stop there, though. Gas continues to fall in from the outer halo, from mergers with neighboring protogalaxies, from the cosmic web of filaments that connect structures across the universe. Some of this gas reaches the center and reactivates the supermassive black hole briefly, but each time the feedback cycle repeats. Accretion, luminosity, outflows, gas expulsion, quiescence. Over time, the mass of the supermassive black hole and the properties of the galaxy's bulge converge toward the M-sigma relation. The equilibrium is reached not through a single event, but through billions of years of iterative adjustment. Different galaxies reach this equilibrium through different paths. A galaxy with a very massive heavy seed, one that grows rapidly through super-Eddington accretion in the first few 100 million years, may overshoot. Its supermassive black hole may become so massive that it quenches the galaxy entirely before the galaxy can grow to match. The result? A relic like NGC 1277, an overmassive supermassive black hole in a small dead galaxy. A galaxy with a more modest seed, perhaps a light seed that grew gradually, or a heavy seed that accreted intermittently, may reach the equilibrium more smoothly. The supermassive black hole grows in tandem with the galaxy, neither dominating nor falling behind. The result? A galaxy like the Milky Way, a modest supermassive black hole, ongoing star formation, a living galaxy. A galaxy that somehow lost its central supermassive black hole through a gravitational slingshot in a three-body merger, for example, might grow without regulation, without the feedback that sets the limit, without the thermostat. The result is harder to predict. Perhaps an overgrown gas-rich system with no clear central structure. Such galaxies may exist, but they would be rare and difficult to identify. The point is this: the final size of the galaxy, the number of stars, the mass of the bulge, the velocity dispersion, depends on the entire history of the interaction between the central supermassive black hole and the surrounding gas. And that history began when the seed formed. Heavy seed or light seed. Rapid accretion or gradual, positive feedback or negative. The initial conditions, the mass of the seed, the gas supply, the halo mass, set the trajectory. The M-sigma relation is where the trajectory ends. One supermassive black hole, setting the trajectory for the entire galaxy. This is the picture emerging from JWST, from Chandra, from Hubble, from ground-based observations with the Keck Observatory and the Very Large Telescope. It is not a picture of simple coevolution, not a picture where galaxies and supermassive black holes grow hand in hand from the beginning. It is a picture where, in the early universe, supermassive black holes can get ahead, where the seed, the initial black hole, can be disproportionately large compared to the nascent galaxy, where that disproportionate black hole can, through its feedback, first trigger and then suppress star formation in the galaxy forming around it. And the final size of the galaxy, the number of stars it ultimately produces, the mass of its bulge, its position on the M-sigma relation, depends on the interplay between that initial seed and the gas supply available over cosmic time. The M-sigma relation, in this new understanding, is not a starting condition. It is an endpoint, an equilibrium that galaxies reach through different paths, some with overmassive supermassive black holes that quenched early, like NGC 1277, some with modest black holes that allowed prolonged star formation, like the Milky Way, some still in the process of adjustment, billions of years after the initial imbalance. The evidence for this revised picture is growing, but it is not yet complete. Several critical questions remain unanswered, and each points toward specific future observations. How common were heavy seeds? If direct collapse black holes formed in only 1 in a million primordial gas halos, then most supermassive black holes may still have grown from light seeds with efficient accretion. If heavy seeds were more common, forming in a significant fraction of early halos, they could dominate the early supermassive black hole population. JWST's ongoing surveys, measuring the fraction of early galaxies with active galactic nuclei signatures as a function of mass and redshift, are designed to answer this question. Current cosmological simulations, including projects like Illustris, Eagle, Simba, and Blue Tides, are being refined to incorporate direct collapse mechanisms and super-Eddington growth. Some early simulation runs with JWST constraints show that default black hole physics in models, physics tuned to reproduce the local M-sigma relation, underproduces high redshift supermassive black holes. Researchers are adjusting, planting heavy seeds of 100,000 solar masses in halos above a critical mass with metallicity below a threshold, mimicking direct collapse conditions. The frontier lies in determining how common or rare heavy seeds were. Can we observe a direct collapse black hole forming? A massive gas cloud collapsing directly into a supermassive black hole without forming stars would produce a distinctive spectral signature, a very hot, infrared-only source in an extremely metal-poor environment. JWST has identified candidates for so-called direct collapse galaxies, but no confirmed detection of a direct collapse black hole forming has been made. Finding one would be definitive evidence. What role do black hole mergers play? If early supermassive black holes merged frequently in the dense early universe, the combined mass could grow in sudden jumps rather than through steady accretion. Gravitational waves from such mergers, from black holes of tens of thousands to hundreds of thousands of solar masses merging at high redshift, would be detectable by the Laser Interferometer Space Antenna, LISA, a planned European Space Agency mission anticipated for launch around 2035. LISA will consist of 3 spacecraft in solar orbit, separated by 2.5 million kilometers, roughly 1.6 million miles, forming an interferometer sensitive to low-frequency gravitational waves. If heavy seeds were common and merged frequently, LISA will detect their signatures. The 2015 detection of gravitational waves by LIGO from merging stellar mass black holes of approximately 30 solar masses inaugurated gravitational wave astronomy. LISA will extend that capability to the supermassive black hole domain. When does black hole feedback flip from positive to negative? The transition from positive feedback, where black hole outflows trigger star formation, as in Henne's 2-10, to negative feedback, where they suppress it, as in massive quasar-host galaxies, likely depends on the mass of the supermassive black hole, the mass of the galaxy, the density and temperature of the gas, and the geometry of the outflows. Some radio observations have found candidate jet-induced star formation in larger galaxies too. For example, jets from the active galaxy Sagittarius A, whose X-ray source was first detected by the Uhuru satellite in 1971, possibly triggering star formation in surrounding gas filaments. The threshold conditions remain poorly understood, and predicting whether an active galactic nucleus will trigger or quench star formation in a given situation currently exceeds our capabilities. What became of the little red dots? These compact, extremely red objects found by JWST at redshifts between 6 and 8, with stellar masses of roughly 1 billion solar masses or less, potentially hosting supermassive black holes of 10 million to 100 million solar masses, appear around 600 million years after the beginning of the universe and vanish by 1.5 billion years. If they are indeed small galaxies with obscured, rapidly growing supermassive black holes, the little red dots represent a previously invisible phase of black hole galaxy assembly. Their disappearance at lower redshifts suggests transformation, perhaps into the progenitors of today's compact elliptical galaxies, or the cores of larger systems built through subsequent mergers. Connecting these high redshift objects to present-day galaxies involves missing pieces. We can observe the beginning. We can observe the end. The intermediate stages remain largely uncharted. And there remains the question of what lies at the center of each supermassive black hole itself. At the heart of every black hole sits a singularity, a point where the equations of general relativity produce infinite density, where our mathematical description of space-time breaks down. We can describe the effects of a supermassive black hole on its galaxy with precision, trace the feedback, measure the masses, map the correlations. But what a black hole actually is at its core? What happens to matter and information that crosses the event horizon remains an open question. A boundary in our knowledge as real as the event horizon itself. It is worth sitting with that fact for a moment. We have spent this entire investigation examining how a supermassive black hole can shape a galaxy, how its feedback controls star formation, how its mass determines the galaxy's final state. At the center of this mechanism, at the center of the object doing all of this work, sits a singularity we cannot describe with our current physics. We know the exterior, we understand the effects, The interior remains hidden behind a one-way boundary from which no information returns. Something fitting about this. The object that may have determined the size of our galaxy is, at its core, incomprehensible to us. The laws of physics as we currently understand them, general relativity, quantum mechanics, have not been successfully unified in a way that resolves what happens at a singularity. A complete theory of quantum gravity would be needed, and that theory does not yet exist. Some questions may simply be beyond what science alone can address, not because they are unscientific, but because the tools we have, powerful as they are, carry edges. At those edges, we find not answers, but more questions. The investigation continues. Each year, the evidence file grows. The James Webb Space Telescope is now in its second cycle of observations, with programs specifically aimed at faint active galactic nuclei in high redshift galaxies using NIR-SPEC and MIRI to identify heavy seeds. Ground-based extremely large telescopes, the Giant Magellan Telescope and the European Extremely Large Telescope, both expected to come online in the late 2020s, will take spectra of the brightest high redshift objects at higher resolution than JWST can achieve. The Nancy Grace Roman Space Telescope, a NASA infrared space telescope planned for launch around 2027, will survey large areas of sky, providing statistical samples of early galaxies with supermassive black holes, helping quantify how common the overmassive phenomenon truly was. Future X-ray observatories like Athena, planned by the European Space Agency for the 2030s, will carry far greater sensitivity to high redshift X-ray sources than Chandra, potentially finding many faint quasars hidden behind dust. The hunt for seeds is now a recognized scientific goal, and multiple observatories across the electromagnetic spectrum are aligning to contribute. Before I present the final summary of this investigation, I want to return to something I mentioned earlier: the M-sigma relation, the fact that it exists at all. Across the observable universe, across billions of galaxies with different formation histories, different merger trees, different environments, different epochs of peak star formation, the mass of the central supermassive black hole and the velocity dispersion of the bulge stars arrive at approximately the same ratio. A power law with an exponent of 4 to 5 and scatter of only a factor of 2. We have a mechanism, the Silk-Rees feedback threshold, that explains how this ratio is enforced. We have observations from the local universe and now from JWST that show us the ratio being established, violated, and eventually restored over cosmic time. We have simulations that can reproduce the relation, at least approximately, when the right feedback prescriptions are included. The deeper question remains, though. Why does this particular combination of physical constants, the gravitational constant, the speed of light, the proton mass, the Thomson cross-section, produce a universe in which self-regulating feedback between supermassive black holes and galaxies is possible? Why are the energy scales of black hole accretion and the binding energy of galactic gas clouds related in such a way that a stable equilibrium can be reached? These are not questions that astrophysics can answer. They sit at the boundary between physics and something else, something that the equations map the edge of, but cannot cross. Science can describe what happens and how it happens. The question of why anything exists at all, why there is something rather than nothing, why these constants and not others, why a universe in which supermassive black holes can shape galaxies rather than a universe in which no structures form at all sits beyond the reach of telescopes and equations. This is not a flaw in the investigation, it is a feature of the investigation. The more precisely we can describe the mechanism, the feedback cycle, the seed formation, the accretion physics, the more sharply the boundary between the describable and the indescribable comes into focus. The equations get better, the data gets richer, and the questions at the edge get sharper, not answered. Sharper. Let me now state, with precision, where we stand. We know that the M-sigma relation, discovered by Laura Ferraris, David Merritt, Carl Gebhardt, and colleagues in 2000, describes a tight correlation between supermassive black hole mass and galaxy bulge velocity dispersion in the local universe. We know that this relation, while it holds locally, did not hold in the early universe, that JWST has revealed systematic deviations, with supermassive black holes consistently overmassive relative to their host galaxies at redshifts above 6. We know that the light seed hypothesis, where supermassive black holes grow from the 100 solar mass remnants of population 3 stars, remains viable but carries strain from the discovery of billion solar mass black holes less than 700 million years after the beginning of the universe. The salpeter time of 40 million years per doubling requires nearly continuous Eddington rate accretion for 500 to 600 million years, a demanding condition. We know that the heavy seed hypothesis, direct collapse black holes of 10,000 to 1 million solar masses, formed through the monolithic collapse of pristine gas clouds in dark matter halos, provides a plausible mechanism for producing these overmassive early supermassive black holes. The idea, first explored by Martin Rees in 1978 and developed by Marta Volonteri and Priyamvada Natarajan, has gained substantial support from JWST observations. We know that the Silk-Rees feedback model, proposed by Joseph Silk and Martin Rees in 1998, explains how a supermassive black hole can regulate galaxy growth through negative feedback, expelling gas when its energy output exceeds the gravitational binding energy of the bulge. The threshold condition, 1/2 V escape squared approximately equals 4 sigma squared, provides the theoretical basis for the M-sigma relation. We know that Amy Rains's discovery in the dwarf galaxy Hennies 2-10, published in 2011 and expanded in 2022 with student Zachary Schutter, demonstrated that supermassive black holes can also trigger star formation through positive feedback. The first direct evidence of a supermassive black hole acting as a builder, not just a destroyer. The 150 parsec filament connecting the black hole's outflow to a young star cluster of tens of thousands of stars, only a few million years old, remains one of the most striking observations in this field. We know that NGC 1277, with its 17 billion solar mass supermassive black hole comprising 59% of the galaxy's bulge mass, represents the extreme outcome of a supermassive black hole that overshot the M-sigma equilibrium, a galaxy arrested in its development by the very object at its center. We know that UHZ1, at redshift 10.3 with a supermassive black hole-to-stellar mass ratio approaching 100%, detected through the combined data of JWST and the Chandra X-ray Observatory behind the galaxy cluster Abell 2744, represents one of the strongest cases for heavy seed formation. We know that the Takela 2024 galaxy at redshift 6.68, with a 400 million solar mass supermassive black hole accreting at only 2% of its Eddington rate in a galaxy of 1 billion stellar solar masses, demonstrates that some overmassive supermassive black holes have already completed their rapid growth phase and entered dormancy. We know that Virgil, studied by George Rica and Pierluigi Rinaldi in December 2025 using JWST's MIRI instrument, showed that seemingly ordinary early galaxies can harbor hidden, overmassive, supermassive black holes invisible in optical light. We know that the little red dots, dozens of compact, extremely red objects at redshifts between 6 and 8, represent what may be a common but previously invisible population of rapidly growing supermassive black holes in small early galaxies. We know that the Event Horizon Telescope has confirmed through direct imaging of M87 star in 2019 and Sagittarius A star in 2022 that the objects at galaxy centers are indeed supermassive black holes described by general relativity. Andrea Ghez and Reinhard Genzel, through decades of tracking stellar orbits at the Milky Way's center, using the Keck Observatory and the Very Large Telescope, earned the 2020 Nobel Prize for proving that 4.3 million solar masses concentrate at Sagittarius A star's position. And we know that the investigation continues. The James Webb Space Telescope observes, peering back to the reionization epoch, the period between roughly 200 million and 1 billion years after the beginning, when the first stars and galaxies formed and their radiation reionized the primordial hydrogen gas. The Chandra X-ray Observatory detects the Event Horizon Telescope images. LISA, planned for 2035, will listen for gravitational waves from merging heavy seeds. The Nancy Grace Roman Space Telescope, planned for approximately 2027, will survey. The Giant Magellan Telescope and the European Extremely Large Telescope will resolve. Athena in the 2030s will see X-ray sources too faint for Chandra. What we do not know, what remains open, is the precise frequency of heavy seed formation, the conditions that determine whether black hole feedback is positive or negative, the detailed accretion history of individual supermassive black holes in the first billion years, the role of black hole mergers in the mass assembly process, and the paths that connect the overmassive early systems to the balanced ratios we observe today. We do not know whether the Milky Way's central supermassive black hole, Sagittarius A star, played a constructive role in the galaxy's early history through positive feedback, or simply grew quietly alongside its host galaxy without significantly shaping its trajectory. And here, at the boundary between what we know and what we do not, we encounter not a failure of inquiry, but a reminder of its limits. We can describe, with increasing precision, what happens and how. The question of why these particular physical conditions, why these specific initial states, why anything at all rather than nothing, extends beyond the instruments, beyond the equations, into territory that science maps the edge of but does not claim to cross. What we are left with is this: a galaxy, the Milky Way, 100,000 light-years across, 100 billion stars, a disk of gas and dust and stellar populations spanning a range of ages, a bulge at the center, dense with old stars. And at the very center of that bulge, in a region you could fit inside the orbit of Mercury, a supermassive black hole. Sagittarius A star, 4.3 million solar masses. An event horizon 12 million kilometers, roughly 7.5 million miles across. If the galaxy were the size of the United States, the black hole would be a coin. Smaller, relative to its host, than almost anything we would consider significant. And yet, the M-sigma relation tells us that this supermassive black hole and this galaxy arrived at a specific ratio. A ratio that galaxies across the observable universe share, despite having different histories, different environments, different epochs of formation. The James Webb Space Telescope has shown us that in the early universe, that ratio did not hold, that supermassive black holes were often overmassive, potentially formed from heavy seeds through direct collapse in dark matter halos, and that their black hole feedback shaped the galaxies that assembled around them. Amy Raines showed us that in small galaxies like the dwarf galaxy Hanize 2-10, supermassive black holes can trigger star formation through positive feedback. The outflow compressing gas, the gas collapsing into new stars, the darkness seeding light. NGC1277 showed us what happens when a supermassive black hole grows too large too fast. The galaxy freezes, its star formation arrested, a relic fossil of an earlier epoch carrying the signature of a 17 billion solar mass black hole that consumed or expelled every gram of gas available. One supermassive black hole. At the center, smaller than the solar system. And the evidence suggests it may have determined how large the galaxy around it became. Not through gravity alone. The gravitational influence of Sagittarius A star extends only a few light-years from the center, a negligible fraction of the galaxy's 100,000 light-year span. Through energy, through black hole feedback, through the radiation and outflows that either compressed gas into new stars or expelled it beyond the galaxy's reach. Through a process described by the Schwarzschild radius, the Eddington luminosity, the salpeter time, the M-sigma relation, the Silk-Rees threshold, the Schmidt-Kennicutt law, and the Bondi accretion rate, equations that trace the arc from a seed black hole in a primordial gas cloud to a dormant engine at the center of a galaxy 100,000 light-years wide. Through a process that began when the universe was young and whose outcome we measure today in the positions of 100 billion stars and the silence of a dormant engine at the center of the Milky Way. The M-sigma relation holds in the local universe. The heavy seed hypothesis gains support from each new observation by the James Webb Space Telescope. The Chandra X-ray Observatory finds supermassive black holes hidden behind dust. The Event Horizon Telescope confirms that event horizons exist, and the investigation into how one supermassive black hole could shape an entire galaxy remains open. Sagittarius A star, 12 million kilometers, 4.3 million solar masses, 1/10,000th of 1% of the galaxy's mass. A coin on a continent. And possibly, according to the evidence now accumulating from the most powerful instruments ever built, the reason our galaxy is the size it is. Not tragic, not triumphant, just true. Or at least as close to true as the current evidence allows. The investigation remains open, the data continues to arrive. And we find ourselves here, in a galaxy that may owe its size to a dark object we will never see directly, observing, measuring, calculating. Reaching across 26,000 light-years with equations and infrared light, trying to understand the thing at the center that may have written our galaxy's story before the first star in the Milky Way was born. Good night.